don't want it to
Say
be
hi.
recorded.
So,
Okay.
so why don't you take your time, do it here, take your time, and I'm going to tell the class something else while you're doing that.
Okay, all right.
While you're setting it up. Okay, the other thing that I want to tell everybody is that on Friday there was a colloquium in which there were some interesting things said. One thing that I was unaware of was that blood vessels become wider when there's more blood flowing through them. In other words, if you have an animal with blood vessels of a certain radius, the animal then has, or if you have two sets of animals, one set of animals has lots of blood flow, the other one doesn't. The blood vessels of the animals that have higher blood flow will increase in radius. Okay. And in fact, the changes are permanent in the sense that anything is permanent in living systems. And so one way to get blood flowing, more blood flowing through one's blood vessels, of course, is to exercise, especially aerobic exercise, where you're breathing a lot and the heart pumps faster and shoves the blood through. The other thing that was also in the lecture, the colloquium last Friday, was the classical result that the flow of a fluid through a pipe of radius r is proportional, of course, to the pressure difference, but also to the fourth power of the radius. So if you combine these two things, you see that somebody who exercises will have higher blood flow. The higher blood flow will increase the radius of the blood of the person's blood vessels, and therefore the flow of blood through the blood vessels will rise as the fourth power of the radius, which also would be growing. So in other words, in the colloquium on Friday, there was a serious scientific explanation of the physics of why exercise is so important. Yes?
So that would mean it would like decrease like blood clots and heart attacks and things like that. They come with like age, for example, like when you're exercising, since it's going to keep those expanded.
Yeah.
It's going to keep you from getting all those different things.
Well, I mean, it's not going to make... As a friend of mine said, if you eat right and exercise a lot, you won't live forever, but it'll seem like it. So, I mean, you'll live longer, you'll be healthier. You'll also be smarter, though, because you see the blood vessels in the brain are very, very thin. And if they expand a little bit, you get more sugar, more oxygen and sugar to the neurons, and so then you're smarter.
I'm going to run before that calc test next Friday.
I've never looked at it. This isn't even my final four.
Don't start working on it.
Okay, so let's see. So I'm going to talk about artificial intelligence some more. I went through the brief history and the experts, something about expert systems last time, and I started to talk about neural networks. So I want to talk a little bit about them, and I actually did a computer experiment, and I found out that there's a cheap way of doing neural networks that's very fast, and on the handwritten data set, that's the standard for testing a neural network, my cheap one came out at 80, it recognized 82% of the handwritten images correctly. Now, an optimal neural network on a supercomputer can do 99%. So I'm not saying that this is the best way to do things, but it's interesting that one gets 82%. And it's so easy to set up, and it's also, I think, perfectly general. You can do it for any system.
All right, it's just a quick question. So,
Oh God, I didn't bring my notes for this part of the course.
It's alright. So I am doing the central limit, and this is the probability function. I'm using it.
Right, right. So the original thing,
Mhm.
you go to 0 to 1, the original distribution would look like this.
Yeah, so I'm trying to test and make sure I can get back the original distribution.
You're trying to what?
Make sure I get back the original distribution when I just have n equal to 1.
Right.
And
So
when
you should get this for n
I
equal
should get
1.
that, but I'm only getting 1/2 of the distribution. I'm only getting this part. And I was just wondering if you could think of any reason why that would be. I don't know if the integration.
So what we had was we had a particular formula. In other words, what you do is you generate a real number that's in the interval 0 to 1.
Yep.
And then you take, I think you set then x equal to 1/2 a cube root or something.
Yeah.
Oh, it's complicated.
Yeah.
Oh, here's the thing. You have to be careful to define this thing in such a way that it's. Do you have the formula for it? And I'll show you how to do it.
I don't.
What's the formula? There's this. You found the formula.
I
right?
did. I can look it up again.
Yeah, look it up again. But the point is, if you use that formula without, massaging it,
Okay. Does it not work?
you could get wrong answers because it.
Okay. So, the integral.
No, I'm just talking about.
Yeah, I know. I just have to, or I think it's all right. Yeah, 4x right. Okay, yeah. So it's 1/2.
This is erased.
1 minus
Cube root or
the
something.
cube root of 1 minus 2x. So that's the inverse of the
Or in this case, okay, so we're going to set r equal to that, where
Yeah.
x is in 0, 1. Okay, so let's get rid of that. Okay, now here's the thing. You wrote a program then to implement this?
Yeah.
Okay.
It's
So
not
what-
that one specifically. It's doing it for generic, but it should be using that one.
All right, so the important thing is if x is less than 1/2, then you just set r equal to 1/2, 1 minus 2x to the 1/3.
Mhm.
But if x is greater than 1/2, then you see this is negative,
Yeah.
and the cube root, the computer might be confused.
Yeah.
So what I did, if x is greater than that, then what you mean by the cube root of a negative number is some negative number. So this is negative, and it's then, okay, so the right thing is to set this equal to 1/2, 1 plus 2x minus 1 to the 1/3.
Okay.
Because then, what this really does is it says, oh, this is negative, I'll take the cube root of the negative number and I'll give you just a negative cube root, and then with the minus sign I'll make it positive. So the other way of doing it is to make the thing positive and take the cube root of that.
Okay.
So I think that might fix your problem.
Okay. Yeah, I just have to figure out how to implement it because I'm trying to make it a generic thing.
All right, let me get back now to neural networks. So as I said the last time, can you turn the camera a little bit? Neural networks have become economically and commercially really important because they can basically be programmed to do reliably anything, almost not anything, but lots of things that a human can do in less than a second. If it takes a human more than a second, then neural networks, current neural networks aren't smart enough to do that. And so basically what happens is that there's a function called, what people normally use is something called ReLU, which is 1/2 x plus absolute value of x. So this is 0 for negative x, and it's just x for positive x. And so the signal, if a given neuron gets input, what did I call it? A1, A2, dot, 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 what did I call it? A sub n. Then the standard thing is to say A is equal to, the output is ReLU of weight 1 on input A1 plus dot, 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 plus WN AN minus B, and that's the output of the neuron. Okay. People used to use a sigmoidal function, sigma of x, but apparently people have found that this is more complicated and it really doesn't help much in one. So that people have switched to ReLU. So now if we're looking at the ELF neuron, then the ELF neuron, of course, I'm saying this is the output, but now if we have a set of neurons, what's actually happening is that the output of the first neuron goes to all of the neurons in the second layer, and the output similarly of the third neuron goes to all of these neurons, and similarly like this. And now, so then you can speak of the input then, or the output. If we say here this is L equals 1, L equals 2, the second layer of neurons, the output of neuron J in level L will be this ReLU. And by the way, does anybody know a better symbol for ReLU? I think something with 3 capital letters is really stupid. All right, this is then WL J1 A1 coming in from the previous level. Okay, it gets a little bit complicated, you see, even writing down just how a particular neuron is going to respond. So this particular neuron with L equals 2 and J equals 3, so this is L equals 2, J equals 3, this guy is going to send out signals, and the signal is going to send out is ReLU of this. These are weights that are arbitrary numbers that you put in, and that's an arbitrary bias. And now here's the basic thing. Suppose you have, see these numbers here, these WLJK and BLJ, these are arbitrary numbers. These are adjustable parameters. And one finds these parameters by training the neural network. And you usually train the neural network with a set of curated data. In other words, let me use Nielsen's example of handwritten numbers. And these are available on the web on a certain data site, which in fact in this, I give the website. So what you can do is you can then train the neural network to discover what these W's and B's are. And in fact, if you have, suppose you have this, suppose you have M layers of neurons, and you have, that's N neurons in each layer. And now you don't need to do that. Many neural networks have different numbers of neurons in different layers. Then you have a lot of parameters. The number of parameters is M times N times N plus 1. Plus 1 is because of the bias. And so suppose you decide that you're going to have 3 layers, and you're going to have 1,000 neurons in each layer. Then it turns out that you have 3,300,000 adjustable parameters. And these are the WLJKs and the BLJs.
So
So
the big M is adjustable parameters?
Excuse me?
The big M is number of adjustable
Yes.
parameters?
And so it's, this is all in the handout.
Okay.
The Apple print program is such that when you do Command P, the next thing you enter, if you're not careful, is the number of copies. And I was entering the page number, which was 716.
That's awesome.
So the printer's in your office, and it's okay because you hear the thing grinding away. But I erased the board before I went in there and found that it was. All right. Don't tell the chairman. So now Eugene Wigner, who was one of the great physicists of the middle of the 20th century, a Nobel laureate, and he wrote a rather nice book on group theory, actually, group theory and atomic structure. Anyway, he said once, he said, give me 5 parameters and I can fit any. Well, this is 3 million parameters. So that's basically the secret of neural networks. It's that when you train the thing with enough data and you have enough neurons, you can basically get it to do anything. And okay. Now, suppose, on the other hand, that you go. So let's see. Can we swing this around? So suppose that you decide, well, this ReLU function, I'm going to replace ReLU by just a linear function. So then, and I'm going to set all the biases to 0. So this would be an unbiased linear network. Well then, ALJ is just WLJK times AK L minus 1. But on the other hand, AK L minus 1, that would be WLJK WL minus 1 KR AL minus 2 R and so forth. So eventually what you have is simply a matrix algebra, a linear thing. That is to say the signal going out is just linearly related to the signals coming in. And the original signals coming in would be the image that you're trying to recognize. Okay? So that's the original signal. So if you have an unbiased linear network, right, an unbiased linear neural network, and I must say, I've been thinking of these neural networks as having the same number of neurons in each layer. You could have an arbitrary number of layers, an arbitrary number of neurons in each layer. You set all the biases to 0 and replace ReLU by just x instead of a half x plus absolute value of x. Then what you've got is that your guess y is just a times your input x. So you're going to be mapping each vector into another vector in a linear way. Now, let's go immediately now to an example. And this is the MNIST website, which, by the way, I hate because all the files are written in a format that is called high-endian, whereas Intel processors use low-endian. And so this website forces everybody to deal with the transformation from high-endian to low-endian. And in other words, convert a binary file from one format to another. And most people haven't done that in years or ever because because everybody uses Intel processors now. Anyway, it turns out that Python can do this, and apparently there's a trick in MATLAB to do it, and presumably there's a Fortran expression, I don't know, to do it. I mean, I used to fool with endians, but I haven't screwed around with binary numbers in many years. Anyway, so in fact, a graduate student gave me a Python, Lady Ma, I don't know, you may know him, Chinese guy. He gave me a Python program which I use to translate these high-endian files into low-endian files. These files then are 60,000 images of handwritten numbers. And they're real images. They're taken from, well, in fact, since you've got a computer open, you've got the handout, right? Right, so if you go to page 704, you can see the website that you can, what the website is if you want to see these files. Anyway, there's 60,000 images of handwritten images of numbers, and each image is a 28 by 28 image. So it has 784 pixels. So it's by no means perfect, but it's sort of okay. And then it also has the labels. It has another file with labels which say that image 1 is a 0 or something, image 2 is a 1 or something, and so forth. Then it has another set, so that's 60,000 labels. Then it has another 10,000 different images and another 10,000 different labels. And this website has been a standard place to test neural networks. Namely, you train on the 60,000. In other words, you show the neural network 60,000 images, and you tell it, you see what it gets, and you say bad network.
Bad network.
It's the wrong label, and so forth. All right. And I didn't tell you how to do this. All right, so I'm going to have to. Well, I'll come back at the end and show you how to do it, since I'm already on this other track. What you can do then is train your neural network with these 60,000 labeled images, and then you can test it on 10,000 other images with 10,000 labels. Okay, now, if, on the other hand, you've got an unbiased linear neural network, it's just a matrix, the question is, what is the optimal neural network? And here, you don't need to train the thing at all. You can just, by linear algebra, figure out what the correct matrix is. Notice that this matrix A is a very funny matrix. It looks like this. This is A, and then X is just this, is just a vector like, well, no, X is actually a vector that looks like that. So X is a 1, X has 784, and you take this 28 by 28 image and write it as a vector, then it's a 784 dimensional vector. And A multiplies it and turns it into, for example, if this is the, by the way, I did this testing in the last few days and found out what the matrix A should be for these 60,000. And then I tested it here, and it got the right digit a little over 82% of the time. What's interesting here is that this, presumably the accuracy would go up if the data set were bigger. And the neural network, I mean, there's no training, it's just instantaneous, it's just a couple of Fortran programs. It does it. But on the other hand, a serious neural network on a supercomputer can do better than 99%, can recognize better than 99% of the digits correctly. So what we have here is a wicked dirty way of doing it. It'd be nice to figure out a cute way to improve it. To push it up closer to 99 without doing a lot of work, but I don't quite want to do that. All right, let me show you what this is. You see, this is not a square matrix, but this is a general theorem in linear algebra, and in my book, in chapter 1, sort of section, I don't know, 31 or something, there's something called the singular value decomposition. And MATLAB has a program that will do that. You just say SVD. In fact, if you enter a matrix in MATLAB, I think you just say SVD of A, and boom, it'll do the singular value decomposition for you. One way of thinking about the singular value decomposition is to say that A is then the sum L equals 0 to 9 of L bar. And what's L bar? Well, first of all, L tilde is just a sum of all of the it's a sum of all the 60,000 image vectors for a given label. In other words, you sum up, you go picking through the 60, computers do it, I couldn't do it, people can't do it, but computers can pick through the 60,000 images and add up all the ones that are correctly identified as 0, 1, or 2, or 3, and then you get 10 vectors here. These vectors, since these vectors are all 784 dimensional, In other words, they have 784 entries. I'm using Dirac notation. Is that okay, or do you want me to explain Dirac notation?
If you could quickly go over it, I haven't seen it before.
You have not seen
No.
Dirac. What about?
Never seen
Okay, all right. Okay, Dirac was a truly remarkable man. So let's suppose we have a vector 1, 2, 3. Well, Dirac would write that, and suppose we call that vector x. Well, Dirac would write that like this. Right? Now, on the other hand, x transpose would be 1, 2, 3. And Dirac would write this like that. And now here's the cool thing. Suppose you have two vectors. Then the dot product of two vectors x and y would be x. Dirac would write it this way. So for example, if x is 1, 2, 3, and y is 4, 5, 6, then this will be, of course, 4 plus 2 times 5 plus 3 times 6. That's the dot product. But one of the things you see that Dirac's notation, by the way, in general, I've been writing real numbers here. In fact, integers for simplicity. If these things were complex, suppose there's an I here, then this would be minus I, because it would actually be transpose complex conjugate, which in physics departments is written ex adjunct. So then x times y in this case would be 4 minus 2 times 5 plus 3 times 6. Okay. Now, so this much of Dirac notation is just an alternative way of writing ordinary matrix algebra. But what is cool about Dirac notation is that you can write an outer product of y with x. And this thing, well, what is it? Well, what's y? Y is 4, 5, 6, and x is 1 minus 2i, 3, commas there. And so what you do here is you just, this is then a matrix, which is 4 minus 8i, 12, 5 minus 10i, 15, 6 minus 12i, 18. So in other words, the outer product of two vectors is then a matrix. And this becomes enormously important in quantum mechanics and quantum field theory. Quantum mechanics, clearly. By the way, there's a very good lecture. Today's Tuesday. Thursday and Friday, there are two very good lectures. There's a French physicist, Alain Aspect, who's coming and talking 3:30 on Thursday, 3:30 on Friday. It's quantum optics, but it's also quantum mechanics, and I recommend that you all go to it and bring your friends. Especially the colloquium. I don't know, maybe the seminar might be a little bit hairy. If it's hairy, just get up and leave. Anyway, he's done all sorts of remarkable experiments in quantum mechanics, and some of the earliest experiments were showing that photons follow their wave functions, and that's how you get interference and diffraction. And then Compton showed that photons actually scatter off electrons like as though they were both particles. And in fact, they are particles. It's that they're quantum mechanically they follow their wave. The wave function tells them where to go, but they're actually tiny particles. Right? So small we don't even know how big they are. And then Davis and Germer scattered electrons off nickel crystals and showed that electrons, which everybody realized were particles, electrons follow their own wave function also, but with a shorter wavelength. These are famous papers that you can get from PhysRev 1923, 1927. And one of the amusing things is that Davis and Germer explained in their paper, back when papers were clearly written, that their research was advanced by an accident. Something exploded in the lab and heated up their nickel crystals so that when they finally cleaned the nickel crystals, the crystals were bigger and let's see, I got the impression reading, maybe you can help me, I got the impression reading the Davis and Germer paper that the interspacing between the nickel atoms in the crystal was getting bigger, and that's why they could see the things. But I think that can't be. It must be simply the crystals were bigger. Do you remember?
I'd imagine it's that the crystals are bigger, but I thought it just had to do with like a dual rearrangement of the structure.
The what?
I thought it was just a general rearrangement of the nickel structure that caused it to work.
Yeah, well, I don't know. Anyway, they were able to see the diffraction, that the electrons were diffracted much as X-rays would be diffracted from nickel crystals. And that's because, in fact, electrons at 300 electron volt energy have wavelengths given by lambda over lambda is Planck's constant over the momentum. This is just ordinary H, not H bar. That is similar to an X-ray. Okay, well, way off the beaten path here. Anyway, LNS8 is doing similar things, but with atoms. But more than just these simple things, he's doing much more sophisticated things with atoms. And so that's really what we're going to. The seminar is 3:30, I think we're in room 190, which is a lousy room for seminars because it's very long and all the space where people could sit is taken up with these stupid tables. Brain dead room.
Is that the one over there next?
What?
Is that the one right over there?
Yeah. In fact, Dunlap and other people did a physics day, and the first thing they did was they got rid of the tables, put in normal chairs, so
That's awesome.
you could fit a lot of people, which is the right way to arrange it. All right, anyway, so what is it that intuitively, I mean, I could show you mathematically, but let's just look intuitively. What would the right matrix be? Well, clearly, if you take L tilde to be just the average of all the images all the ways people wrote the number L, and then you write L bar as L tilde over the inner product of L tilde with L tilde. In other words, this makes it unit square root. This normalizes it. So you normalize it, so that's what L bar is. And so this is the correct form for the optimal matrix that gives you, it's the best you can do with a simple matrix. In other words, linear, unbiased neural network. And as I said, it gets a little better than 82%. Okay, so now let me get back to the general idea of a neural network. What you normally talk about is the squared error. So let's talk about the squared error on a certain training sample. I've got these B's. What are these B's? Well, I think maybe my phone here. Can I use somebody's pen?
Yeah, first. This is a pencil.
Yeah, that's sure. So this is the squared error. So this would be 1 over n times the sum k equals 1 to capital N, and then a sum I equals 1 to c, and this would be the prediction of the kth this is the prediction of the kth. See, what the neural network in general is doing, the task of the neural network in the case of handwriting analysis, is to take each image and to classify it as a 0, 1, or 2, 3, up to 9. More generally, it's to take image K and to say that it's that it belongs in class I. And one might associate a probability with that. And the correct probabilities then are delta I of L of xk. In other words, if the correct label is L, then the probability should be 1 for I and 0 for all the other ones. And you then take this thing squared. So this is the error, the squared error that a neural network will make when being tested on capital N images or capital N stimuli xk and trying to fit it into C categories, or to identify which of C categories that image belongs in. So that's the error, and what the standard thing to do then is to say, okay, what's the gradient of E squared? Oh, now I know what the V's are. Let me get my other eraser here. The V's are all these parameters. So the V's are the parameters which in the case of 3 layers of 1,000 neurons each are 3 million parameters. So what you do is you take the gradient of this thing, which is to say partial of E2 with respect to V1, partial E2 with respect to V sub m, where m might be 3 million in a serious neural network. At Google, it might be 3 billion. And Chinese may be higher than that. And what you do then is you say, I'm going to change parameter I in the following way, minus partial E2 partial VI. So you just, where epsilon is some tiny number, tiny positive number, and this is a matter of judgment, how big the number is. In these things, by the, well, no, all right. I was about to give the rule for Monte Carlos. In Monte Carlos, this thing is called a step size, although this isn't the formula one uses. But one picks a step size, and the rule of thumb is you want a big step size because you want to move fast, but you want a small step size because you want to make a reasonable acceptance rate. If you have a very tiny step size, you'll have a very high acceptance rate. If you have a big step size, you have a slow acceptance rate. So what you normally do is you tune the acceptance rate to a half, so that half the time your change is accepted. Here, you just pick a small number, epsilon, and that's a matter of judgment that comes with experience. But obviously, this is a something you can't do with your fingers. You have to have, especially if you're using ReLU with biases, then, and there are 3 million of these things, then you have to have the computer compute this. One way of course, doing it is to say, all right, the way I'm going to compute this is I'm going to measure the error by changing VI by a tiny amount epsilon and see what happens. That will give you that partial derivative. But that means that you have to run the thing on a suitable number of samples, X's. You take a certain subset of the training set and you compute E squared with VI, and then you compute E squared with VI minus epsilon, and you see what the difference is, and you compute the derivative numerically. Another possibility is you compute the derivative in general analytically and write some Godot for Fortran or C or whatever program that evaluates numerically the derivative. That is, I don't look forward to doing that. But of course, it's only that may be why my impression is that people use 1 layer, 2 layer, or 2 layers, or 3 layers. I haven't heard people talk about 1,000-layer networks. So part of the reason, I don't know, you know, I'm not, don't worry. I have not worked in this field, so I'm not really experienced, but that's the impression I get, that 3 layers is a lot. So let's see, what, well, I think maybe then what I ought to do is show you, by the way, do any of you know Fortran? C?
Yeah.
Oh, you know C?
Yeah.
Okay. Well, you know, you can take a Fortran program and translate it into C.
I never touched Fortran.
It's
No
Fortran.
one uses Fortran anymore.
Huh?
No one uses Fortran anymore.
That's not true. That's a myth. Fortran has certain advantages. One is it's very easy to program. The second advantage is that if somebody else reads a Fortran program, the person can read it and understand it much more easily than the C program.
Well, if you want that, then use Python.
Third reason, because Fortran is so straightforward, easy to learn, easy to write, the compiler can understand the program and can optimize it. Whereas you give a C program to an optimizing compiler, the compiler can't figure out what tricks this guy is showing off. notation I'm using. And so for numerical work, Fortran is very good. The advantage of C++ is that if you are in a big group, because of the modular structure, because you can have modular Fortran 90 or Fortran 210, 2010, whatever. But
By modular, do you mean like object-oriented, or?
yeah, I think so.
Okay.
I'm not quite sure what all the implications of C++ are.
I mean, the main thing about C++ compared to C is that it is object-oriented.
Yeah, well, you can have modules in Fortran.
Okay.
And anyway, for numerical work in a small group, Fortran might be better than C++. For a large group, C++. But I tell you what, I'll put the programs on the website so that if any of you want to look at them, you could probably read it and translate it to C, because Fortran is so easy to understand. I'll also put the Python programs that I got from Lady Mike. I sent email to the guy who had that website. I sent email to Nielsen also. And I said, do you know of a website where they have these things in Intel format? No. And so then I sent an email to the guy who wrote the thing, and he wrote back, no, just write a simple program.
My friend might know some databases.
Huh?
I have a friend who uses neural networks for a lot of stuff. He might know some databases for this sort of stuff.
What Nielsen said to me was that translating one database into a format that you can use is a huge waste of time in the neural network community. All right, well, I think maybe what I ought to do is show you, just as a mathematical exercise, how you would optimize the neural network in the case where it's unbiased and linear. I didn't go through this, I just eyeballed it. I said, well, it's got to be this. And that got me 80%. Let me now derive why it would be that. And this will show you how, if you had, this would act, if you actually only, well, it's hardly a neural network where you just have one layer. So, of course, if you don't want to see this, I could skip to the next chapter.
Oh, what's this?
All right, well, so, let me see. I don't want to change notation too much. What we'll say is that or equivalently, and let's see, what else? We want to minimize yi minus, why don't we call it ti, absolute value squared summed over I, right? where TI are the true images of the true labels for the ith vector. Maybe I should put an I there for the ith. Well, I certainly don't want an I. Well, I should. Okay. Then, so this is and so these two things are effectively a vector. So this is AX. This is summed over I, of course, times its adjoint, which would be TI, say, transpose minus A transpose. Whoops. XI transpose. And what we want to do is we want to differentiate this with respect to each of the AIs, each of the elements of the AIs. And so we'd set 0 equal to this derivative, and by symmetry this would have to be something like this. If we differentiate with respect to a particular element there, then in fact this would have to be so this would be I, K. This would be, what am I doing? So this would be XK, the Lth one of them, minus TIL. Oh, no, there wouldn't be anything there, sorry. And I think this is basically telling us what's going on here, namely that this term has to be 0. And so that's just saying that what we want is AX, say the Lth one of these, to be TL. That's what we actually want. But we can't quite have that because these TL is, in the case of the handwriting example, this is an L-dimensional vector, and this vector is 784-dimensional. And so what we need here is effectively the pseudo-inverse. Now, I didn't bring my notes on pseudo-inverses. Nobody has a copy of my book here, huh? All right, let me run down to the office and grab it.
Just naming my short research report that you probably had to grade.
Oh, wait, what'd you write it on?
The Hoover Dam.
The Hoover Dam?
Some call it a dam.
That's your research report on Tyler?
It's about magnetometers.
I learned so much in my classes.
Mag-
This weird
Magnetometers?
Magnetometers. I don't know how to pronounce it. I've never used them before. I've never even heard the word pronounced correctly.
Do you need a ride home?
No, that's picking me up.
Yours is only every day. It doesn't generate that much electricity.
I haven't figured that out.
Working, not the way I wanted it to, but it works. So,
That's good. It takes me like
like,
30
I wanted
minutes.
it to
to
You should-
follow.
you should name that my
all
family
over
folder.
there, and then it would plot the data
Give me a
to the
name.
axes. But I just have it so that when you click the button, it locks the axes up, so that there's no confusion about where the data is supposed to go.
Okay.
How do you pronounce that again? So I don't look stupid again.
Magnetometers, I'm pretty sure.
It's not a word to pronounce.
Okay, so the pseudo-inverse, what we want then is XL should be TL times a pseudo-inverse, which would be a dagger times it depends on whether the columns or the rows are linearly independent. So let's see. This A matrix looks like this. So the columns are certainly not linearly independent, but the rows are linearly independent. So if the rows are linearly independent, then the correct expression is A dagger inverse. Actually, I don't know if this makes all that much sense. I thought this was easier than it is, because I didn't actually calculate, I didn't go through the derivation, I just decided the right answer is that and programmed it in Fortran, and it was good to 82%.
It was a pretty good answer for a guess.
Well, thanks. But, well, the singular value decomposition is always something like this. It's going to be something called L bar summed with some eigenvalues, and the eigenvalues here are all going to be 0 or 1, so they're all going to be 1 actually. And so now what should we use from the training set as a vector if we want it to have maximum overlap with the true, if we want it to have maximum overlap with the handwritten images that are for the number L, then, you know, clearly the thing is what I said originally, namely that you set L tilde as just the average of all of these vectors. And then you normalize it. So it's, this thing is then sum L and 1 over, well, leave out the 1 over n because we're going to normalize it subsequently. So this is sum over L from 0 to 9, and then this would be a sum of the xi's, well, call this L tilde and then divide it by square root of L tilde, L tilde. So that's what works at a level of 82%. And it makes sense because these guys, these are the images that are correctly identified with the letter L. So these are 60, they wouldn't be 60,000 actually, because in fact it would be 6,000, because there's 6,000 zeros, 6,000 ones, 6,000 twos, and they're altogether 10 digits, and so it would really be up to 6,000. And I'll work out the algebra of this and put it in my class notes over the next couple of days. So what do you want to see on Thursday? Shall I continue with this or move instead to things like order, chaos, and fractals?
Yeah, that sounds like
Yeah.
cool.
I want to do fractals.
The order, chaos, and fractal sounds pretty cool.
Yeah, or is somebody strongly wanting more of this?
Fractals sound good to me.
Okay.
Where's Kate?
I have
All right, so
I
I'll
have a
move
quick
to
question.
that. Huh?
I have a quick question.
Yeah.
So,
Actually, I owe various people candies. Somebody want to try to open this?
I think Cayman is
All of it.
the right woman for the job.
Yeah, why don't we let
She
you
just
open it?
loves those.
Um,
I can't imagine anything stopping her.
Try to open it though in such a way that there's as to not damage. This one I don't care about, but the under one I care about
Okay.
because it's got a see there's a thing in there. See that hole? That hole is handy for carrying it.
You can do it, Cayman. All right. So,
So what's your question?
It's just a vocabulary question because I remember seeing this in the past, but I just want to double check. In your brief history of artificial intelligence,
Yeah.
In the 1997 section, you mentioned the bulldozer approach.
What? Say it again?
You mentioned the bulldozer approach.
Yes, that's the IBM approach, yeah.
So that's when you just analyze every possibility to a very long extent, right? What's the bulldozer approach on this?
Well, it's whatever, you did a marvelous job, thank you. Here, let's give you a couple more.
Wow.
Also, doesn't anybody else want the handout? Did everybody get a handout?
Yeah, but we have a few more hundred.
Just in case.
So what's the,
What's the bulldozer approach?
I guess it's that they had some enormous supercomputer that they called Watson. And they just had Watson read all kinds of documents, and they somehow tried to. I mean, I don't know what they did because I certainly didn't program Watson, but part of what they did may have been, there's this thing called big data.
Yeah.
And so they read in a gazillion documents and organized them in a way such that if a question came in, they could retrieve information. For the case of chess, what they did was I think they just analyzed a gazillion chess positions, chess boards, possible chess boards, and computed what the best next move would be. Now, what somebody did, and maybe the Watson people did this, I don't know, but what some people did was it was started out as a checker, which is much simpler than chess, of course. Some man programmed two computers to play checkers with each other, or maybe it was one computer to play checkers with itself. And this computer started out, the first few, this was, maybe 20 or 30 years ago, the first few times the guy played against the computer, the guy was good enough at checkers to beat the computer. But after the computer started playing with itself, and it could play thousands and thousands of games with itself, the computer got absurdly good at checkers. And it could be that in chess, they had one computer playing against another. I don't
Oh,
know.
it's a trainer.
I don't know how they did it, but
There's AlphaGo now, which is really cool. They trained a computer to play Go.
yes, that's right.
Yeah.
That's pretty
There's
And
really
they
good
did, and they did
documentary
it
on
by
it.
having one computer play against the other, or play against
I
itself?
forget exactly. I mean, it's a neural network. I know that much.
Yeah.
Also, Chef Watson is another very entertaining thing.
Chef in the sense of cooking?
Yeah, they have an AI put together recipes.
That's pretty awesome.
Oh,
It's online.
That
You
is-
can mess with
that
it.
is
You can give it
dangerous.
like specific ingredients
Oh,
in a
okay.
category.
They
I don't
limit it
know
to
what
things
the
that are non-poisonous, right?
Yes, it is all food. It is all consumables. It is all things you can eat safely. Whether you want to eat them is a different question.
That's awesome.
All right, I think we can turn it off.
Well, thank you.